today's session. So Professor Babis Anastasiou, or they put his title, so Perturbative Techniques. So please, Babis.
Yeah, thank you. Can you hear me from the microphone? Yes, right. Yeah. So thank you very much for the invitation. It's a real pleasure to be here in this fantastic celebration of 50 years of QCD. I would like to also associate the celebration with another celebration that we should have. It is a celebration of not only understanding QCD or having discovered QCD, but also of what we have explored beyond QCD. And this, of course, has happened with the classical proportional experimental effort that has taken place over the last decades and culminated with the discovery of the Higgs boson, and on top, having turned the Higgs boson into a particle that we can do precision physics with, and we can understand what perhaps lies beyond the standard model as well. This plot from Atlas has been already shown to you yesterday, but I thought it would be nice to see it again because it shows how well they can measure the Higgs cross-sections in various production channels. And what you see overlaid in these plots is the theory predictions of the types that Thomas and Raja showed you these days. And you see, once again, the amazing agreement that we have between the two comparisons between theory and experiment. So what it is good for us to recollect at this moment is how and why we are able to actually match in this race between theory and experiment the experimentalists, right? And I think we owe all of this luxury of being able to do precision predictions to very good foundations. I mean, nature has been grateful to us. It is asymptotically free, so we have an possibility to do perturbation theory. We also figure out, what we can measure so that we can apply perturbation theory. So the concepts of infrared safety were developed. And also, we figure out for high-value processes, like the ones where you produce a very massive object or you have a large momentum transfer, how we can separate from the Feynman diagrams the non-perturbative contributions from the perturbative contributions with factorization theorems. On top, this was supplemented with the superb measurements at the LHC and the previous colliders. Thomas gave examples of having used experiments also at low energies, not only the more fancy experiments that they can give a lot of information. This provides us with structure functions, with coupling constants, masses, and things like that. But finally, an ability to compute perturbation theory quantities at very high orders. So I would like to focus on that right now. But before I go further, I would like to make a statement about how this must have been looked upon at the beginning of this story of doing perturbative calculations. Already Keith and others mentioned this historic paper of 79 with Keith, Altarelli, and Martinelli, where in Drell-Yan, they just figure out there are very large perturbative corrections. The story repeated itself later on when Sally Dawson made another historic calculation of the Higgs cross-section at the beginning of the 90s. Then she also found a very large perturbative correction. And what I very much liked in the conclusions of Sally's paper was that she was very confident to make qualitative assessments of what the meaning of this result was. So she could say, yes, the cross-section increases. We can be sure about that. But she did not have the information. She could not have had the information that it would lead her to make very bold quantitative statements of the type that we are doing routinely nowadays. When first calculations of these processes at Drell-Yan and Higgs came up at next to next living order, then you could see very much that the language changed and the statements became quantitative. What I appreciate very much in Van Irven's conclusions, when he computes Drell-Yan at next to next living order, and then he tries to put it in context, he points out that now the data agrees with experiment. He calculated order alpha strong square, but what he says is that the order alpha s is needed in order to agree with experiment. This shows you that whenever you compute an order higher, you get confidence of the result before. And you still should be a little bit shaky because we are doing perturbation theory into the unknown about what happens afterwards. So now, of course, oh, I didn't mean to do that. We have gone to these processes, as Thomas explained, at next to next living order, but also there, at a different level of precision, at the percent precision, we see that when we go from one order to the other, we have to think how to interpret the results. So for Drell-Yan and Higgs at the NQ below, then you can see some larger corrections that you would not, that what you would anticipate otherwise. So this has been the background. So, and inevitably we were forced to go very much in high orders in perturbation theory because of necessity, because we really needed to match the data. Let me visualize these corrections. I have two examples that they show how dramatic this could be. This is the Higgs decay, not a production process. And I have put in different boxes the corrections that you have at each order in perturbation theory as a percent of the total answer that you have. And you see that when you go from leading order to next to leading order, you do have a very big correction as well. The pattern looks good, and it is convergent, although from next to next to leading order to the next to leading order, the decrease of the size of the correction is not that big. But overall, it is convergent. But imagine having only the first two boxes in your availability. You will not be sure about what is happening. And if you look at Higgs production, the next to leading order part is bigger than the leading order. So then you start wondering, if you only had the first two pieces alone, you start wondering, what is the meaning of perturbation theory in such a setup? Admittingly, this dicing of perturbative orders that I have displayed there, it's not unique. You know, you can decide to absorb things in the alpha strong, that they belong to higher orders, and you can shuffle things around from one order to the other. So this separation is not the only way, and you can separate it, and you can make these relative sizes to change from one situation to the other. But this is one reasonable, typical separation that we do nowadays in 2020 of how we compute each order in perturbation theory. And this is how we would see it right now if we did this calculation for the first time. OK. So this is the situation. And when we added and piled up all the orders, and when at the end of the day we piled up also electroweak corrections, or we understood better how to do massive loop integral calculations, we ended up with an amazing agreement between theory and experiment. But bear in mind, whenever you see this comparison, there are some decades of work that they have gone, not only in the experiments, but also on the perturbative side. And because we have both reached this stage, we are confident in making statements about new physics these days. We know that there is not much of what we would have expected, but we can look at smaller and smaller possible effects for new physics. Thomas and Raja explained very well the benefits of doing these high-order calculations with several examples, just to give you a picture of what to expect in terms of precision at each perturbative order. Leading order is just qualitative. Next to leading order, you should expect an around 30% precision. Next to leading order, you should expect an around 10% precision. And next to leading order, you should expect less than 5% precision. So this is the gains when you pile up the orders, but of course, you also have to account for the fact that you have more difficult calculations to do. What I would like to do today is to give a small flavor of these difficulties and the techniques that have been developed. I will try to stay away from topics that Thomas already explained. So I will focus on a few different aspects. And what I will also try to do is to detour to other fields. I will tell you a little bit about how these techniques can be used in a possible way in cosmology. And then I will come back to particle physics. But what is really needed in this type of perturbative computations are three elements. You need physics, you need computing or computational methods, and you need advanced mathematics. And there have been excellent ideas and methods over the years. Now there is an order that these elements combine themselves traditionally or in many examples. So you start with a physics calculation, then you know that you have to develop your computational techniques, then you realize that the math is not there, you have to discover a new math, and then you realize that even the math is too complicated, so you need physics to come back and simplify it. And at this point, I would actually like to praise the contribution of UCLA with V, and also his long-standing collaborators, Lance Dixon and David Kosover, who will speak afterwards, that they actually made a school out of trying to put the physics into perturbative calculations and simplify perturbative calculations by utilizing as many physical principles as possible. So I will not talk very much about it because I know David is coming up afterwards. So let me try with examples to give a sense of the, let's say, the size of the problem that we have to face, and then to sketch how these things are getting solved. So this is one of the diagrams that you will see. Okay. Okay, sorry. Yeah, this is one of the diagrams that contributes to Higgs production via bottom fusion that has been in the last few years calculated. And it's a cut diagram, forward scattering amplitude. And I would just like to count how many things you have to compute for such a diagram. This is one of the order 5,000 diagrams. I actually generated all of them just to see how many they are, but you know, I didn't want to give the exact number just to make multiplications easier. And this diagram is not just one object that you have to compute. It contains many other integrals. Of course, it depends on your preferences or techniques on how to break this diagram down to things. One possible way is to see this diagram as a contraction of a tensor integral. You have 6 fermion propagators. Each one of them gives you a momentum slashed with a gamma matrix. You can think of it as a contraction of a loop momentum and some spin structure. And then you can actually write down one projector that maps it to scalar integrals. And this projector is going to have order 500 diagrams, 500 integrals. So for one of the 5,000 objects, you have to compute 500 things in there as well. So this is quite a bit. Now, the story doesn't finish there. So let's simplify so that I can give you the flavor of it. this integral. And I will make a toy example out of it, okay? For each propagator that you see, I will put a k squared minus m squared denominator. There are 10 of them. I will also make delta functions to behave like propagators. And for each numerator, I will put a square root of k squared minus m squared. So this, if you think about it, think of it as being somehow the superficial degree of divergence integral that you would get. And I will assume all momenta are the same, and I will integrate over only one momentum. Okay? So in this toy example, you see that you create, out of such a diagram, you create a tadpole integral. And you know how to compute it. It is a simple ratio of gamma functions. Okay? But if you think of the gamma function, how you compute the gamma function itself, the way you do it is with recursion. So you say gamma of x is x plus 1 is x times gamma of x. So if you apply that, then you see that this integral, in order to compute it essentially, it creates many other integrals in between. So if you think that you know gamma of 1, which is the simplest object possible, and this is corresponding to what we call in modern day language master integral, then you have created all of these integrals before in between. So the combinatorics of it is quite impressive. Now you can argue that this is a gamma function, and there are two messages. You create many integrals, but the other message is that you simplify. At the end, you only needed to compute one thing. And this propagates, and we exploit it if we go to further higher orders. Sorry, if we have integrals with their full complexity. They are not going to be simple gamma functions, but they are going to be products or ratios of gamma functions summed over infinite indices, indices of an infinite range. These are hypergeometric functions. Most of them, for modern loop integrals, are uncharted hypergeometric functions. We don't really know all of them. However, this factorial recursion property persists in there, and it takes the form of difference equations. They are not diagonalized. You cannot go from one to the next to the simpler with a direct step. You have to do some work for that, but this exists for all loop integrals at all orders in perturbation theory. So for example, we are confident that if we pile up to a box diagram propagators and we write it down as hypergeometric functions and simplify it, we will get the same story, the same result as, we will get a simplified result. So we will get the box with unit parse propagators and some bubbles after that. So this is something we have to exploit. We have to use this type of recursion to compute less integrals. The question is, can we do this systematically? Here comes the physics. It has come to our rescue, and actually huge satisfaction because of its physicality at one loop order. We can show nowadays that one loop amplitudes are a simple collection of bubbles, tadpoles, and triangles and box master integrals. And what happens on top is we can see that these coefficients multiplying these master integrals are not just random outcomes of recursion, but they organize themselves into sums of products of three amplitudes. So there are many gentlemen that are present, and they contributed to this to this fantastic result here. So this is where the physics comes in to save us. Practically what we are saying is that amplitudes or integrals are essentially determined by their singularities. Their singularities correspond to propagators being on cell. If you have propagators on cell, then things factorize in a loop into three amplitudes. So that is one of the revolutions, and there is a huge progress in the field trying to get this idea to work at higher orders. And already at 2-loop orders, we have seen some amazing theoretical work and results in this direction. It is unknown how this program is going to continue at higher orders, at next to leading order calculations, for example. But when physicality does not work, we can intensify our computations, and we can go back to these recursions of the factorial simplifications that I was showing you before. So this is also systematic. There is an algorithm that actually has been used in a vast majority of NNLO and NQBLO calculations by Laporta, which solves these recursion identities from the bottom up and can always give us some result. However, the result is messy and the result can be lengthy. And there are limitations because you are computing something with a factorial cost. Okay, one thing I want to mention is that these recursions are formulated usually for loop integrals, but you can use Katkovsky rules in the reverse direction, and you can also apply them to cuts. And with this, we can also do simple inclusive cross-sections or differential distributions like the ones that we have seen in the examples before by Thomas. What I want to show, okay, so how far can we go? Well, you know already how far we can go. I'm sorry, I think I'm missing one slide. Yeah, okay. The 2 slides are reversed, but I apologize for that. So how far we can go? You can have, with such type of techniques, calculations of differential cross-sections at next to leading order in perturbation theory. For lack of time, I'm not going to, sorry. I will get the handle of it, sorry about it. I would like also to discuss one more aspect rather quickly. And this aspect is about what comes in the answer, not only when we compute the recursion and the reduction to master integrals, but also when we calculate the master integrals. There are many techniques for that, and some of them, the most successful one, for example, is the method of differential equations pioneered by Thomas and Remedi. What happens is that we map the master integrals to some polylogarithmic functions. Amazingly, at one loop, there is only one polylogarithm we have to know, and this is the dilogarithm. At 2 loops, there is a lot of systematics in there. So these polylogarithms have been studied exhaustively, and also by mathematicians and physicists together. But what happens is that we do make progress in classifying them and finding the relationships, but at the same time, as we compute more and more complicated things, it seems that we also discover new types of polylogarithms. And this is kind of a difficulty, because if you know what the result of your answer is, instead of calculating, you guess the answer, and then you match it to the result. And here, if we don't have a finished closed system of polylogarithmic functions that all loop integrals map to, then we cannot do it always. Anyhow, we have discovered quite a few things in perturbation theory, and I told you how we have used them and what we have achieved with them in particle physics. Let me now cross a field and try to go to cosmology. In Switzerland, there are very strict instructions when you try to cross a field. You have to be very, very careful. And the instruction that I like the most is that if the grazing livestock approach, then stay calm and practically get out of there, but, but without turning your back to them. So if you ask me a cosmology question in what I say, I will stay calm, quiet, and I will tell you about loop integrals, okay? So, so this is how I'm going to do it. So why should we care about cosmology as QCD people? Well, because they also have a very extensive and ambitious precision physics program. They are going to have a lot of data, understanding in fine detail the large-scale structure of the universe. And this is good for precision physics, and perhaps the tools that we have in QCD are applicable there as well. In fact, a lot of the groundwork has been done already with the development of effective field theories that they predict this type of large-scale structures evolutions. For the regimes where the density fluctuations are not very large, and there is a big part of them in their observations, you can apply perturbation theory around the linear approximation solution. And the result looks like this, for example. It looks like Feynman diagrams, okay? This is the two-point correlation function. This is the so-called power spectrum in momentum space. And you can represent it as Feynman diagrams. The leading order Feynman diagram is a propagator, which represents the linear solution of the equations. And this Feynman diagram and this linear solution is now part of the loop corrections with some vertices as well, okay? So this would be the next leading order calculation. Now, let me go into the vertices. The vertices, if you write them out, they look like in the denominators, which are the most important for us in terms of calculability, like massless propagators. If you go, though, to the propagators, as I told you, the propagators are the linear solution for the two-point function. And this depends on the cosmology. So it has a shape like this. So this doesn't really look very much like propagators that we have. So at a face value, you would say this problem is not for us. On the other hand, it can be made. I don't have much time. There has been one good solution attempt in the past on how to do it, but it really doesn't really map us completely to the integrals that we know how to do. So I will try to explain how we do it ourselves a little bit differently, and it really maps us to very familiar loop integrals. So this is the propagator that we have in Feynman rules. This is its shape as the function of the momentum, okay? And this, we cannot compute it. But imagine that instead of that, we had the Breit-Wigner. Okay? It's not through cosmology, the Breit-Wigner, but if I had a Breit-Wigner, I would know how to do it, because it's massive propagators, and we have seen them in perturbative QCD calculations. Okay, this would be a very crude approximation. You will say that Breit-Wigner is nothing like that, so I will get a wrong answer. But I can pile many of them. And in fact, what you can do is you can fit this power spectrum, the linear power spectrum, to some functions which eventually give you massive propagators. Then you can apply reduction techniques. I will not really say much about it anymore because I'm running out of time. And then you can really reduce this object down to master integrals that we know, like bubbles and tadpoles. This is for the two-loop power spectrum, for the one-loop power spectrum, for example. If I wanted to do a more complicated function, then I would have one more master integral, a bubble, a tadpole, and a triangle. And here comes something that we have learned from QCD. If I want to do an n-point function, well, the master integrals in 3 dimensions, everything here is 3-dimensional, remain the same. It's a tadpole, a bubble, and a triangle. Okay? So in this approach, we can claim that we can compute in the effective field theory of the large-scale structure all correlation functions at one loop. And we have created the algorithms that they do that. We have already published one paper, and there was a follow-up phenomenology paper that they used the bispectrum, the 3-point function, to extract useful information like Hubble constants and the other parameters of the lambda CDM. And they are very competitive with CMB, and actually it's very good phenomenology, very nice constraints. They are offering very good new information in there. The future is also very good because there will be more data coming in, and all of this precision is going to be improved by big factors of 2 or more. Let me say that one does not really need to stop at 2 loops, at 1 loop. We can do with the same things 2 loops. Very quickly, let me flash, a result that we just obtained. We computed 2 of the diagrams. If the conference was taking place 3 months from now, I would have had all the diagrams, but it's not. And I think this is a good way forward. Okay, let me now come back to QCD in a very small amount of time that I do have. And the reason to also be back to QCD is that there is a high luminosity LHC, and there is a lot of data that it is coming up, and a lot of ambition. So we want to see the Higgs couplings improved in precision by a factor of 2, for example. But there are also processes that the experiments have shown us that they can measure for the first time pretty well. So rare processes of complicated final states. I have 2 examples here. One is TT-bar Higgs production, and the other is tri-boson production. So let's say WWZ. Okay, the simulations for this for this calculation for these processes are at next to leading order, and if we think in terms of how much more work we need to do to improve the precision to next to leading order, so to go to 2 loops, then we realize that we have to pile up in our abilities to compute integrals and amplitudes 2 more kinematical scales, 2 more masses than what is the state of the art. So this is going to be challenging for the analytical approach, and we have to offer some alternatives. Okay? So here what I would like to do. I would like to advocate that perhaps we should explore a purely numerical avenue for this type of computations. So what is the idea? Okay? The idea is something that we also applied in the cosmology 2-loop calculation. I didn't really explain it very much, but the master integrals there, in our language, analytically, would correspond to some elliptical functions that we don't know how to compute or identify. And the way that we computed the cosmology results was numerically, because these cosmology integrals, they are finite. They are Euclidean. They converge. They live in 3 dimensions, and they don't have singularities. They may have integral by integral, but we know how to deal with that. In the sum, they don't have. Okay? So here is an idea. How about we try to do numerically completely 2-loop integrals? Okay? What is the benefit of that? I may oversell it unintentionally. I don't want to hide any complications, but one of the great points from doing it like this is that when you calculate 2-loop integrals in momentum space, integrating numerically, you always have to do a fixed number of integrations. It is 3 per loop. You could say it's 4 per loop, but 1 you can do it analytically very easily. So it is always 3 per loop. So no matter what is your process, you will always have, for any 2-loop process, 6 integrations to do. Okay? But there is an abstraction. This is infrared divergences. And I would like to actually go back to physics, to the physics that actually was important for QCD at this generation, the physics that shows factorization of infrared divergences, and see if this physics can help us and become a computational tool. Okay, so let me very quickly try to say what are these divergences. Everybody knows here, but just in order to be able to make the discussion, I would like to flash again a little bit the story. So when you have loop integrals, you have propagators. Propagators have poles, and these give rise, under certain conditions, to singularities. Okay? So if you have one propagator, oh, I keep doing that. Then each propagator furnishes 2 poles, and these are potentially singular. However, in many cases, you don't need to worry so much because you can deform the contour integration of around these poles, and you don't have a true singularity. There are those cases in massless gauge theories like QCD that you cannot do that. So if you have massless particles, then when these particles become soft, the poles become one on top of the other, and I'm not good at it. And then they pinch the contour, so you cannot deform around it. So this is what we call a pinch singularity. If you have collinear particles, poles from one propagator aligns on top of another from another propagator, the collinear other particle, and again you have a pinch singularity. So you cannot deform the contour of integration away from that. So these singularities, they have to be removed somehow. We know what happens to them. At the end of the day, if you remove all of these singularities and accumulate them together, you will get a physical picture, which tells you that the scattering amplitude, where you have a large momentum transfer, factorizes in color space, but it factorizes in factors where the soft exchanges or the soft singularities are in the red part, red factor, and for each incoming colorful particle, you have some function, some factor, which is called the jet factor, and the remaining is not divergent. The soft and the jets are singular, they have the singularities, but the remaining is hard. It lives in 4 dimensions completely happy. So then this is an all orders result. And in principle, if we could use it, we could try to extract the hard function with it. And if one is thinking about QCD 100, maybe we can figure out a way to do this at all orders in perturbation theory, because this holds at all orders in perturbation theory. So, okay, how can we use it? We can invert. We can multiply with the inverse of these factors, the inverse of the jet function, the inverse of the soft function, the amplitude. And then we should be getting the hard part. Well, if it's so simple, why don't we just do it? Okay? And let's go and see inside the integrand to see what happens when we do that, right? So we say that the amplitude, which is an integral over some integrand, should factorize into the soft and the jet functions. I'm sorry about torturing you with that. Soft and the jet function. And here we have multiplied the original amplitude with the inverse of these factors. And this should be finite in 4 dimensions. So the idea would be that we do this numerically, and this we do it analytically. But these are universal factors. We need to do them once and for all somehow. Okay? So this is how this should work. Now, this is at all orders. If you expand it out, then you get, for this blue part, some perturbative series at leading order. The hard part is the 3 amplitude. At next to leading order, it's the 1 loop amplitude minus some counter terms, and so on and so forth. Okay, so this is what you want to get at the end. But what is the problem? Well, when we do this inversion, we have to be very careful, okay? Because yes, this blue hard part will be finite in 4 dimensions, but it may be not finite for a Monte Carlo integration. Why is that? This is because the cancellations may not happen what we call locally. So if you have a big plus infinity in one part of your integration domain and a minus infinity in another part of your integration domain, you have achieved nothing, okay? What we have to achieve is to pile up the singularities so that they cancel point by point in the integration domain. Okay, so this is the extra work that we have to do. And I'm very glad that George Sterman has this vision, and he has been the person who drove the proof factorization. Because what we have to do right now is that we have to go back to these proofs and remove the elements that produce non-localities and make everything to be completely local. Okay, I think I don't have very much time, but let me just say only 2 things. I'm yellow. I will take 3 minutes, promise. Okay, so 3 things. One thing that we want to exploit is the fact, so how factorization works. It works very simply at some simplistic level. So what you notice is that when particles become collinear, so when gluons become collinear, then they get an unphysical longitudinal polarization. And then word identities tell you that longitudinal polarizations, since they are unphysical, they have to be expelled from the probability amplitudes. And they cannot really be completely expelled. They just amount to a correction to an external leg. So this is the essence of factorization. At 1 loop, this works effortlessly. At 2 loops, however, there are 2 things that they happen. First, if you have emissions of collinear gluons of a hard vertex, for example, then the gluon is not entirely longitudinal, but it has also a polarization which is the momentum of this subgraph here, the loop momentum of this subgraph here. So we coin this momentum, this polarization, a loop polarization. If you integrate over this loop, as for example it happens in Wilson coefficients of Sept, then you don't see that because you will project it to the momentum of the gluon after this integration. But before that, locally, this still exists. The other problem is that word identities at higher loop orders, they also produce zeros, which are not local. So if you attach a collinear gluon everywhere in a loop, then you will see that it is a difference of 2 terms. And this integrates to 0, but this is not allied to 0. So just to tell you that for gluon-gluon fusion to 2 loops and to colorless Van der states and QQ bar to colorless Van der states, we have found solutions for these things. And we have managed to do to create integrants for the hard function which are directly integrable with Monte Carlo integration. And finally, to flash a very new result that it was obtained in this technique, we do QQ bar to 3 photons not completely. We do one gauge invariant part, the NF part. This came to my mailbox. I'm doing physics by mailbox sometimes. It came to my mailbox this morning, so it's a very, very preliminary result. But we managed to compute a part of the two-loop amplitude. What I want to point out here is that we are very confident that we will be able to make these photons off-shell. Actually, it is better for us. Just we wanted to compare with the literature, and that we will be doing next, and we started with that. So I think this has some promise for the future. OK, I'm sorry I'm overrunning, but conveniently, I will not have to answer many questions. These are my conclusions. I think it's fair to say that we have developed a lot of know-how for perturbation theory in QCD, which is extremely important for the physics precision program at the high luminosity LHC and other colliders. But there are opportunities also outside collider physics, and I showed you an example in cosmology. If we want to keep the pace up, we have to infuse to our knowledge more ideas and more techniques. And I hope that using infrared factorization can be one of those techniques. Thank you very much for your attention.
So then questions for Marek?
Thank you for the illuminating talk. My question is about the applications to large-scale structure.
Yeah.
So when you do Feynman integrals in quantum field theory, you make heavy use of Lorentz invariants, and which is not there in LSS. So how do you deal with that?
So I have not dealt with that because, as I said, there is an effective field theory for that, the effective field theory of large-scale structure. And I believe that...
That theory is Lorentz invariants?
No. But still, it is... if you want to do perturbation around the linear solution, then this is how it looks like.
Okay, yeah, I'm going back to this collinear singularities. If compare it with, say, let's say, for simplicity, let's consider QED with in the limit with massless electron. So it would be an example, right? Collinear singularity.
QED with massless electron, you said.
Yes.
Yeah.
Yeah. Okay. There, it's a kind of KLN theorem, whatever, because we know what cancel out collinear singularity. What is cancel out, it is the process where in the initial state you have first you have just one electron, then you have electron and photon, and then there is absorption of this photon, and it is this process of absorption of electron. It's okay with factorization. It doesn't contradict it, but it tells you that then depends on how we form the packet. In these Fock spaces where we have combination of electron plus photon and so on. And in particular, in this case, for example, in the simplest case, it would depend on the distance where the electron was produced. You see, because you're producing electron, in perturbation theory, we produce electron at some distance, and then, it means that it's in this way of shell, right? And it has some number of photons associated with it, and then those photons could be absorbed later on. And I am trying just to find out contact with your analysis. That's why I'm asking. I'm sorry.
So no, yeah, thank you. The one thing I want to say is that you are thinking at the level of cross sections, right? And
no, it doesn't matter. It could be say Q bar goes to
sure.
Gamma is okay.
Okay.
Because it's still initial quarks, right? And the question is how they are prepared.
Yeah. So first of all, let me say that there are many versions of the factorization theorems.
Yeah.
And in this particular one that I'm interested in, we are talking at the level of scattering amplitudes or you don't need to, I mean, you don't.
What I'm saying, it's not specific for cross section. It could be, you can say it amplitude, it doesn't matter, but then it would be still a linear combination of, say, electron plus photon. So you can formulate it like in QED for emission, soft photon, you can calculate at the level of cross section, but you can calculate it at the level of amplitude as well.
Right. Well, so what is the problem?
Okay, no, because when you show diagram, I do not see this stuff, and as I said, this infrared contribution, which cancel out infrared, comes from the absorption of initial gluons, and I don't see it there, and that's why I ask you.
In here, all of these exchanges are in between.
Right, but it's not related to absorption of initial stuff.
So you want to absorb it on itself. This is what you say.
Right. Of course, you can say that the process of preparation you already took into account, but in terms of diagram, I do not see it.
Yeah, in the jets there is a soft component.
Yeah.
And then you have to separate the two.
Okay.
But yeah.
Okay, thank you.
I think you want to accept some coherent state in the end.
Yeah, right. But it is coherent state, right? In physically, it is coherent state, the packet, right?
Sure.
Right.
Yeah, so thank you for this really beautiful and thought-provoking talk, at least for me. So I want to mention that, you don't have to go beyond QCD to think of applications of this heroic body of work, is that even in the field of something like generalized parton distributions, I don't think people are really thought through, all of these kinds of contributions. And I think it really starts to make a difference because you try to understand the structure of poles and so on, and that relates in certain cases to chiral physics that one has to take into account. So I don't think that has been really worked out fully, and I think these techniques are extremely valuable in thinking through those problems as well. So just a comment.
Yeah, no, thank you.
So I think there's a lot within QCD itself that these techniques, beyond just the precision level of calculations that you're thinking about. But
sure.
Yeah.
So if there are no more questions, then thank you again for the